Look up at the night sky, what do you see? A scattering of stars, the glow of distant planets, the hazy streak of the Milky Way, but beyond that familiar view lies a universe teeming with enigmas so profound, they challenge everything we think we know. Black holes that warp the fabric of reality, dark matter weaving its invisible web through galaxies, whispers of parallel dimensions brushing against our own, these are just a few of the cosmic puzzles that keep scientists awake at night. And yet, for every mystery, there are theories daring enough to unravel them, ideas so bold they border on science fiction, but what if they're not fiction at all? Today we're diving into 30 of the most mind-bending theories that could finally explain space's biggest secrets. Some are backed by cutting-edge research, others feel like they've leaped straight from the pages of a cosmic thriller, but all of them share one thing: the power to rewrite our understanding of the universe. Picture this: a black hole isn't just a destructive void, but a gateway to another reality, or that dark energy, the force tearing our cosmos apart, might be the echo of a long-dead universe. These aren't just wild guesses, they're the frontiers of human imagination, where science and speculation collide in the most thrilling ways possible. So why does any of this matter? Because every great discovery starts with a question, a what-if that refuses to let go. Centuries ago, we thought the stars were fixed lights glued to a celestial sphere. Now we know they're suns so distant, their light takes millennia to reach us. What truths are we just one theory away from uncovering? Whether you're a space enthusiast or someone who simply gazes up and wonders, this journey is for you. By the end, you won't just see the night sky differently, you'll feel it, as if the universe itself is whispering its secrets, waiting for us to listen. Ready to begin? Let's go. Imagine if everything we could see, planets, stars, even galaxies, made up just a tiny fraction of reality. That's the unsettling truth behind dark matter, an invisible substance that doesn't emit, absorb, or reflect light, yet holds the cosmos together with its gravitational grip. Without it, galaxies would fly apart, their stars scattering into the void like marbles dropped on the floor. The evidence: spiral galaxies spin so fast that their visible matter alone couldn't keep them intact. Something unseen must be anchoring them, something that makes up roughly 85% of all matter in the universe. But if we can't see it or detect it directly, how do we even know it's there? The answer lies in the way dark matter bends the fabric of space itself. Like a hidden hand tugging at the edges of a blanket, its gravity warps the path of light from distant stars, a phenomenon called gravitational lensing. Astronomers use this cosmic trick to map dark matter's distribution, revealing vast, intricate webs stretching across the universe. Yet the biggest question remains: what is it? Two leading candidates dominate the search. First, WIMP, weakly interacting massive particles, theoretical heavy particles that barely interact with normal matter, except through gravity. Think of them as cosmic ghosts, drifting through walls, planets, even you, without a trace. The other contender, actions, ultra-lightweight particles so tiny they behave more like waves than solid matter. If they exist, they could solve not just the dark matter puzzle but other quantum mysteries too. But here's the twist: despite decades of hunting, neither WIMP nor actions have been definitively caught. Underground labs, particle colliders, even space telescopes have come up empty-handed, leaving scientists to wonder if dark matter is something even stranger. Could it be primordial black holes, forged in the chaos of the Big Bang, or particles from an unseen shadow universe, overlapping with ours? Every failed experiment tightens the mystery, pushing us closer to a revelation that could rewrite physics itself. Because dark matter isn't just missing mass, it's a clue to the universe's deepest workings, hidden in plain sight. But what if we've been looking for dark matter in all the wrong places? Some scientists argue that the answer isn't hidden particles at all, it's a fundamental flaw in our understanding of gravity itself. Enter MIND, short for modified Newtonian dynamics, a theory that suggests gravity behaves differently at cosmic scales than the equations of Newton or Einstein predict. Instead of invoking invisible matter, Min proposes that the extra force holding galaxies together comes from a tweak to the laws of physics. Picture a rubber band stretching farther than expected instead of assuming someone's pulling on it. Min says the rubber's properties change when you pull hard enough. It's a radical idea, but not without merit. In certain galaxies, Min predictions match observations eerily well, without needing dark matter's ghostly presence. Yet Min isn't without its own puzzles. While it explains some galactic rotations flawlessly, it stumbles over larger cosmic structures, like the way galaxy clusters collide. Here, dark matter's gravitational fingerprints are unmistakable, leaving Min to patch together ad hoc fixes. And then there's the bullet cluster, a cosmic smash-up where visible gas and dark matter visibly separate, like a car crash scattering debris in two distinct piles. No modification of gravity easily explains this, forcing Min supporters to propose hybrid theories. It's a reminder that even the boldest ideas must bend to the universe's stubborn evidence. Another contender lurking in the shadows, primordial black holes, hypothetical leftovers from the universe's explosive first second. Unlike the black holes born from dying stars, these ancient relics could range from the size of atoms to mountains, peppering space like invisible breadcrumbs. If they exist in vast numbers, their collective gravity might mimic dark matter's effects. The beauty of this idea lies in its simplicity: no new particles, just cosmic fossils we've yet to dig up. Some researchers even speculate that these black holes could solve two mysteries at once, accounting for dark matter and seeding the supermassive black holes that lurk in galactic centers. But hunting them is like searching for needles in a universe-sized haystack. Occasionally, one might pass in front of a star, bending its light in a telltale flash, a microlensing event. Surveys have spotted a handful of these anomalies, but not nearly enough to explain dark matter's dominance. And there's another wrinkle: if too many small black holes existed, they'd disrupt the delicate cosmic microwave background, the afterglow of the Big Bang. So far, the universe's baby photos show no such scars. The deeper we dig, the stranger the possibilities become. Could dark matter be made of exotic quantum knots in spacetime, known as topological defects? Or particles trapped in a hidden dimension, forever beyond our reach? Each untested idea carries its own allure and its own risks. Embracing Min means rewriting gravity's rulebook. Primordial black holes demand we accept a cosmos teeming with unseen monsters. Yet this is how science progresses, by chasing down every lead, no matter how outlandish, until the universe reveals its hand. After all, history shows us the truth is often wilder than fiction, and in the case of dark matter, we might be one bold theory away from a revolution. We've scanned the cosmos for decades, listening for alien radio signals, searching for distant megastructures, and all we've heard is silence. This eerie absence is the heart of the Fermi Paradox. If the universe is so vast and ancient, teeming with billions of potentially habitable planets, where is everyone? The numbers suggest we should be drowning in extraterrestrial civilizations, yet the void remains stubbornly quiet. It's a contradiction that forces us to confront some chilling possibilities. Maybe we're missing something fundamental, or maybe the universe is hiding a truth darker than we've dared to imagine. One terrifying answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar scales. Think of it as a cosmic sieve. Most civilizations get caught in it, vanishing before they can colonize the stars. The scariest part, we don't know if we've already passed the filter, like surviving an asteroid impact or the invention of DNA, or if it's still ahead of us. Climate collapse, nuclear war, runaway AI. Any could be the wall that crushes civilizations before they leave their cradle. If that's true, the silence isn't just puzzling, it's a warning. Then there's the zoo hypothesis, the idea that advanced aliens are deliberately avoiding us, treating Earth like a protected nature reserve. Picture ants in an ant farm, unaware their glass walls were placed by unseen hands. Proponents argue that interference could disrupt our natural development, or worse, that we're not yet interesting enough to contact, but critics counter with a brutal question: could every civilization in the galaxy agree on such a hands-off policy? One dissenting species breaking the rules would flood the universe with signals, yet the silence holds. Another grim possibility: self-destruction is inevitable for intelligent life. Technology might be a double-edged sword. Every civilization could reach a point where their power outpaces their wisdom. The same tools that let us broadcast to the stars could also engineer our demise. If this pattern holds universally, the cosmos might be littered with the ruins of civilizations that burned too bright, too fast. Radio telescopes might not pick up alien chatter because the airwaves go quiet just a few centuries after a species discovers them. But not all explanations are so bleak. Maybe we're simply too early. The universe is 13.8 billion years old, but the best days for life could lie ahead. Most stars won't even form for trillions of years. We might be among the first civilizations to emerge, pioneers in a cosmos still waking up, or perhaps the answer is simpler: space is mind-bogglingly vast. Signals could be washing over Earth right now, too faint or too slow to detect with our current tools. The nearest star system is 4 light-years away, a whisper in galactic terms, but still an eternity by human standards. The paradox forces us to grapple with our own fragility. Are we alone because life is vanishingly rare, or because intelligence is a fleeting spark in the dark? Every unanswered signal, every silent exoplanet, is a clue. And as we push our telescopes and probes further, we're not just searching for aliens, we're searching for our own destiny. Will we find neighbors among the stars, or will the universe's silence become our mirror? The answer might redefine what it means to be alive in this cosmos. What if we're searching for aliens the wrong way? For decades, SETI, the search for extraterrestrial intelligence, has scanned the skies for radio signals, assuming advanced civilizations would broadcast their presence like cosmic radio stations. But what if they've moved beyond primitive radio waves, or worse, what if their signals are so alien we don't even recognize them? This realization has sparked a thrilling shift in the hunt for technosignatures, physical or energy-based traces of alien technology. And one of the most tantalizing clues might be hiding in the shadows of distant stars. Enter Dyson spheres, hypothetical megastructures built by civilizations harnessing the full power of their sun. Imagine wrapping a star in a vast shell or swarm of solar panels, capturing nearly all its energy. To us, such a star wouldn't twinkle brightly, it would glow faintly in visible light while blazing in infrared, the waste heat of an unimaginable engineering feat. Astronomers have already flagged dozens of stars with these bizarre infrared signatures, like KC 8462852, nicknamed Tabby's star, which dims unpredictably as if something, maybe a partially built Dyson swarm, is passing in front of it. But here's the catch: maybe we're too fixated on Dyson spheres as we imagine them. An advanced civilization might not build clunky solid shells, but instead use something far stranger, like a fleet of star-orbiting supercomputers or black hole-powered engines. Some theorists even suggest aliens could manipulate space-time itself, bending light in ways we'd mistake for natural phenomena. If that's true, the signatures we're looking for might be staring us in the face, disguised as cosmic oddities we've already catalogued and dismissed. There's another blind spot in our search: time. The universe is ancient, and civilizations could rise and fall in the blink of a cosmic eye. What if we're detecting the ruins of long-dead empires, Dyson spheres crumbling, their energy harvests long since silent? Or conversely, what if we're the primitive ones, too early to the party? The truth is, we might not need to look for aliens in the present. Their relics or their precursors could be scattered across the galaxy, waiting to be read like fossilized footprints in the cosmic sand. This is the new frontier of SETI, a hunt not just for signals, but for the fingerprints of intelligence woven into the fabric of the universe itself. From star lifting to quantum communication networks, the possibilities are as vast as they are strange. And if we find nothing, that silence might be the most profound message of all. The cosmos isn't just hiding its secrets, it's daring us to think bigger. Black holes aren't just cosmic vacuum cleaners, they're the ultimate paradoxes of nature, places where the laws of physics as we know them break down spectacularly. At the heart of this enigma lies the black hole information paradox, a puzzle so profound it's pitted quantum mechanics against Einstein's theory of gravity in a battle with no clear winner. It all starts with a seemingly simple question: what happens to information when it vanishes into a black hole? According to quantum mechanics, information, the fundamental blueprint of every particle, can never truly be destroyed. But black holes, with their bottomless gravitational pits, appear to erase it from existence. This contradiction isn't just theoretical nitpicking, it threatens to unravel our understanding of reality itself. Enter Stephen Hawking's revolutionary insight: black holes aren't entirely black, they slowly leak energy in the form of Hawking radiation, a faint glow of particles escaping their grip over unimaginable timescales. Here's the catch: this radiation is random, carrying no trace of the matter that fell in. Imagine burning a book and claiming the ashes still contain its story. Hawking radiation seems to do the equivalent, reducing stars, planets, and even entire civilizations to thermal noise. If true, the universe would have a serious case of cosmic amnesia, violating quantum physics' most sacred rule. This dilemma spawned two radical solutions. First, the holographic principle, which suggests that all the information swallowed by a black hole isn't lost, it's smeared across its event horizon like a celestial fingerprint. Picture a three-dimensional object projected onto a two-dimensional surface. The data is compressed but preserved. In this view, the universe might fundamentally be a hologram, with black holes acting as cosmic hard drives encoding information in their surfaces. It's a mind-bending idea, but one that neatly sidesteps the paradox by declaring information never truly enters the black hole, it's just stored in an unexpected way. Then there's the firewall theory, a far more violent proposal. It argues that the event horizon isn't the smooth gateway Einstein predicted, but a seething wall of high-energy particles obliterating anything that crosses. Think of it as the universe's failsafe. Instead of information vanishing, it's shredded into unrecognizable fragments at the boundary, but this comes with its own problems. Firewalls defy relativity's prediction that falling into a black hole should feel uneventful: no fireworks, no drama, until gravity's tidal forces take over. If firewalls are real, Einstein's theory needs a major rewrite. The stakes couldn't be higher. If information can vanish without a trace, our entire framework for physics, from quantum computing to the birth of the universe, rests on shaky ground. But if black holes preserve it in some bizarre holographic code, we might be staring at the key to a grand unified theory, a Rosetta Stone for decoding spacetime itself. One thing's certain: solving this paradox won't just clarify black holes, it'll redefine what we know about existence, and that's a mystery worth chasing, no matter how deep the rabbit hole goes. What if consciousness isn't just a byproduct of the brain, but a fundamental feature of the universe itself? This is the radical premise of panpsychism, the idea that consciousness permeates all matter, from the tiniest particles to the vast structures of the cosmos. It sounds like philosophy meets sci-fi, but some scientists take it seriously, especially when confronting quantum mechanics' strangest behavior. Take quantum entanglement, where particles instantly influence each other across vast distances, defying classical physics. Einstein famously called it spooky action at a distance, But what if the spookiness arises because particles possess a rudimentary form of awareness? Imagine two electrons choosing to mirror each other's states not through some hidden force, but through a shared flicker of proto-consciousness. The implications stretch far beyond lab experiments. If consciousness is woven into the fabric of reality, it might explain why the universe appears fine-tuned for life. The so-called observer effect in quantum mechanics, where particles behave differently when measured, could hint at a cosmos that responds to awareness. In this view, stars, galaxies, even black holes might participate in a vast, interconnected network of experience. Picture the universe not as a cold, mechanical clockwork, but as a living, sensing entity where every interaction carries a whisper of subjectivity. Critics dismiss this as speculative, and rightly so. There's no direct evidence that electrons feel or choose, but panpsychism offers elegant solutions to stubborn problems. For when it sidesteps the hard problem of consciousness, how subjective experience arises from brute matter, if consciousness is intrinsic, like mass or charge, the mystery dissolves. It also reframes the Fermi Paradox. Maybe advanced civilizations don't build Dyson spheres because they've learned to harness consciousness itself, bending spacetime with thought rather than machinery. The wildest twist, some interpretations suggest that quantum phenomena like entanglement only appear mysterious because we're seeing fragments of a deeper, conscious unity. In this vision, separation is an illusion. The universe isn't a collection of isolated objects, but a single, self-aware whole. It's a notion that bridges ancient mysticism and cutting-edge physics, challenging us to reconsider not just how the universe works, but what it is. Whether panpsychism holds up or not, it forces science to confront a haunting possibility. Reality might not just be observed, it might be observing itself. Consider for a moment that everything around you, the stars, the atoms in your hand, even your thoughts, might not be real in the way we assume. This is the core of the simulation hypothesis, the idea that our universe is an artificial construct, an ultra-advanced digital reality created by some unfathomable intelligence. It sounds like the plot of a sci-fi movie, but surprisingly, it's gained traction among scientists and philosophers, one of its most vocal supporters. Elon Musk, who famously stated the odds we're living in base reality are 1,000,000,000 to 1, but what actual evidence could possibly support such a staggering claim? Start with the fabric of spacetime itself. At the tiniest scales, reality appears pixelated, like a cosmic image zoomed in too far. Quantum mechanics reveals a world where energy isn't continuous, but comes in discrete packets called quanta, suggesting the universe might operate on a kind of resolution limit, just like a video game rendering graphics. Even more telling, the speed of light could function as a processing speed cap, preventing the simulation from overloading. Think of it like a computer limiting frame rates to avoid crashing. And then there's mathematics, the uncannily perfect code underlying everything. The universe follows elegant equations with precision, as if programmed by a meticulous coder. From the Fibonacci sequence in flower petals to the gravitational dance of planets, nature's patterns feel suspiciously like optimized algorithms, but the hypothesis isn't without holes. If we're in a simulation, why would the creators leave glitches visible at the quantum level? Wouldn't they smooth over the pixels? Some argue these imperfections are deliberate, a sort of Easter egg left for advanced civilizations to discover. Others propose that the simulation's complexity requires trade-offs, like a computer sacrificing graphics for processing power. There's also the troubling question of why a civilization would bother simulating us at all. Maybe we're ancestors being studied, or mere entertainment for post-biological beings. The most chilling possibility, we might never know. If the simulation is sophisticated enough, it could prevent us from detecting its boundaries, like a dreamer unable to wake themselves. But here's the twist, The very act of questioning whether we're in a simulation could be part of the program's design. After all, what better way to test a simulation's realism than to see if its inhabitants start doubting their own existence? Whether the hypothesis holds up or not, it forces us to confront a humbling thought: reality might be far stranger than we're capable of imagining, and that uncertainty in itself is a kind of liberation. Black holes suck everything in, but what if the universe has cosmic exits as well as entrances? That's the mind-bending premise behind white holes, the hypothetical twins of black holes. While a black hole's gravity traps anything that crosses its event horizon, a white hole violently repels matter, spewing it outward like a cosmic geyser. Picture a black hole in reverse: nothing enters, only escapes. General relativity allows for such objects mathematically, but do they exist in reality? Some theorists suggest gamma-ray bursts, the most energetic explosions in the universe, could be white holes erupting after lying dormant for eons. Others speculate they might be the other end of a wormhole, a bridge through space-time itself. Speaking of bridges, let's talk wormholes, those legendary shortcuts through the cosmos. Einstein and physicist Nathan Rosen first proposed them as Einstein-Rosen bridges, mathematical quirks where two black holes connect, creating a tunnel through folded spacetime. The catch: traditional wormholes would collapse instantly, crushed by their own gravity. But what if they could be stabilized? Enter exotic matter, a theoretical substance with negative energy that could prop a wormhole open like scaffolding. If it exists, traversable wormholes might not just link distant places, they could link different times. Step in one side, and you might emerge a century in the past or future. The implications are staggering. Wormholes could turn time travel from fantasy into physics, though with caveats. The energy required to sustain one would dwarf anything humanity has ever produced. And then there's the paradox problem: going back in time to alter events could unravel causality itself. Imagine killing your grandfather before your parent was born. Would you simply vanish? Quantum mechanics offers a bizarre fix: parallel timelines. Every trip through a wormhole might spawn a new universe, where history branches like a tree. White holes and wormholes remain speculative, but their allure is undeniable. They challenge our grasp of reality, hinting at a universe far more interconnected and far stranger than we've dared to dream. Whether cosmic exits or space-time shortcuts, these phenomena remind us that the universe's greatest mysteries might not lie in the darkness, but in the bridges we've yet to find. The Big Bang is often described as the universe's dramatic birth, but what if it wasn't the beginning at all? Enter the Big Bounce, a theory that rewrites cosmic history by suggesting our universe didn't emerge from nothingness, but from the collapse of a previous one. Picture a cosmic heartbeat, an endless cycle of expansion and contraction where every big crunch gives rise to a new Big Bang. This isn't just wild speculation, it's a mathematically viable alternative to the singularity, one that erases the need for a mysterious starting point and replaces it with something far more elegant: rebirth. The key lies in the fate of dark energy, the mysterious force accelerating the universe's expansion. If its strength weakens over time, gravity could eventually reverse the process, pulling everything back together in a fiery collapse. But instead of ending in oblivion, that collapse might reach a point where quantum effects take over, causing space-time to bounce like a compressed spring rebounding. The result: a new universe bursts forth, inheriting traces of the old one's structure, cosmic echoes of a past existence. Some models even suggest that black holes from the previous cycle could seed galaxies in the next, creating a faint genealogical thread between universes. Cyclic cosmology goes further, proposing not just one bounce, but an infinite series stretching eternally into the past and future. Imagine a celestial phoenix, forever dying and being reborn from its own ashes. This vision solves one of the Big Bang's biggest puzzles: why was the early universe so perfectly tuned for complexity? In a cyclic model, each cycle cleanses the cosmos, smoothing out irregularities and resetting conditions, meaning our universe's delicate balance might not be luck, but the result of countless previous iterations refining the cosmic fabric. Yet the Big Bounce isn't without challengers. Critics point out that entropy, the universe's tendency toward disorder, should accumulate with each cycle, making successive universes increasingly chaotic. Why then does ours appear so finely ordered? Some theorists counter that quantum gravity effects during the bounce could reset entropy, like shuffling a deck of cards back to randomness. Others propose that information from past universes leaks through the bounce, leaving subtle imprints in the cosmic microwave background, ghostly fingerprints waiting to be decoded. The most tantalizing clue might lie in gravitational waves. If a previous universe existed, its collisions of supermassive black holes could have rippled spacetime in ways that persist through the bounce. Future observatories, like the Laser Interferometer Space Antenna, might one day detect these primordial tremors, offering a glimpse beyond the Big Bang's veil. Until then, the Big Bounce remains a breathtaking possibility, a universe without end or edge, where every ending seeds a new beginning. And if true, it means our cosmos isn't just a one-time event, but a single note in an infinite cosmic symphony. What if every choice you've ever made, whether to turn left instead of right, say yes instead of no, spawned an entirely new universe? This isn't just the stuff of sci-fi, it's the spine of the multiverse theory, the idea that our cosmos is just one of countless others, each with its own laws, histories, and maybe even versions of you. Scientists don't just entertain one flavor of this concept, they've categorized it into 3 dizzying levels, each more mind-bending than the last. Start with level 1, infinite space. If the universe stretches on forever, and evidence suggests it might, then somewhere far beyond our observable horizon, identical copies of Earth and you must exist. Think of it like shuffling a deck of cards long enough. Eventually, the same sequence repeats. In an infinite cosmos, particles can only arrange themselves in so many ways before duplicating entire galaxies, civilizations, even individual lives. The catch: these doppelganger universes lie eternally out of reach, separated by distances so vast, light from them will never reach us. Then there's level 2, bubble universes. Picture a cosmic pot of boiling water, where each rising bubble is a self-contained reality with its own physics. This stems from eternal inflation, a theory where spacetime expands exponentially, spawning pocket universes like froth on an endless ocean. Some bubbles might have stronger gravity, others with no stars at all, wildly different rulebooks written into their very fabric. Here's the kicker: these bubbles could collide, leaving scars in the cosmic microwave background. Some researchers claim they've spotted these bruises, like fingerprints from a neighboring universe nudging ours in the distant past. But level 3 is where things get truly surreal, the quantum multiverse. Every time a particle faces a choice of decaying or not, spinning up or down, the universe splits, creating parallel timelines branching like a tree. This isn't sci-fi writers riffing, it's the many worlds interpretation, a serious attempt to explain quantum mechanics weirdness. In one branch, dinosaurs never went extinct. In another, you took that job abroad. The unsettling beauty: every possible outcome plays out somewhere, meaning there's a reality where you're a Nobel laureate, and another where you're a llama herder in the Andes. So why does any of this matter? Because the multiverse might solve physics' greatest embarrassment, cosmic fine-tuning, our universe's constant gravity's strength. The mass of electrons are dialed to impossible precision. Tweak them slightly, and stars wouldn't ignite, or atoms couldn't bond. It's like winning the lottery a billion times in a row. The multiverse offers a humbling answer: if every possible configuration exists, we simply live in the rare bubble where life is possible. No divine hand, no luck, just the brute statistics of infinity. But not everyone buys it. Critics argue the multiverse is untestable, more philosophy than science. If alternate realities are forever cut off, how do we prove they're there? Others counter that the theory's predictive power, like explaining fine-tuning, gives it weight, even if direct evidence eludes us. And then there's the existential whiplash. If every choice spawns a new universe, does anything truly matter? The answer, ironically, might lie in the very fact that we are here, in this branch, asking the question. The multiverse doesn't dilute meaning, it sharpens it. After all, in a sea of infinite possibilities, this version of you is the one shaping this reality. And that in itself is a kind of cosmic magic. Close your eyes and imagine the universe as a cosmic movie screen, a flat, two-dimensional surface projecting everything you see, touch, and experience into a three-dimensional illusion. This isn't just a thought experiment, it's the heart of the holographic principle, one of the most radical ideas in modern physics. The theory suggests that reality as we know it, the depth of space, the swirl of galaxies, even your own body, isn't truly three-dimensional. Instead, it's a hologram, a shimmering projection encoded on a distant, two-dimensional boundary at the edge of the cosmos. And the strangest part, this isn't science fiction. It might be the key to solving black holes' deepest mysteries and unifying gravity with quantum mechanics. The seed of this idea sprouted from an unexpected place: black hole thermodynamics. When a star collapses into a black hole, all the information about its composition, every atom, every molecule, seems to vanish behind the event horizon, violating quantum mechanics' ironclad rule that information can't be destroyed. But in the 1970s, physicist Jacob Bekenstein made a startling calculation. He found that a black hole's entropy, a measure of its hidden information, isn't proportional to its volume, as you'd expect, but to its surface area. It's as if all the data swallowed by the black hole gets compressed and smeared across its boundary, like a cosmic hard drive storing files on its shell instead of inside. Stephen Hawking later confirmed this, showing that black holes emit radiation and slowly evaporate, but the information they consumed isn't lost, it's transformed, imprinted on the escaping particles in a way we don't yet understand. This led theorists to a jaw-dropping leap. If a black hole's interior can be described entirely by information on its surface, could the same be true for the entire universe? Picture a glass sphere with a movie projected inside. The images appear to have depth, but they are all generated from data on the sphere's inner surface. In this view, the universe might work the same way. The three-dimensional reality we experience could be a holographic projection from a two-dimensional source code at the edge of space-time. It's a concept that bridges string theory and quantum gravity, suggesting that the fabric of reality isn't built from particles or strings, but from bits of information, tiny, vibrating pixels of space-time. But how would this even work? Enter string theory's most enigmatic playground, anti-de Sitter space. This hypothetical universe, shaped like a hyperboloid, has a boundary where quantum field theories can describe gravity's behavior in fewer dimensions. In the late 1990s, physicist Juan Maldacena proved a mathematical equivalence, a duality between a gravity-filled five-dimensional world and a four-dimensional quantum theory on its boundary. It's like discovering that a 3D video game is secretly being rendered by a 2D computer program. If our universe shares this duality, it would mean every event inside it, every supernova, every heartbeat, is just a shadow of information processing happening on a distant, flat surface. Critics argue that our universe isn't an anti-de Sitter space, it's expanding, with dark energy driving galaxies apart, but some theorists propose a workaround. What if the holographic boundary isn't out there, but in our past? The cosmic microwave background, the afterglow of the Big Bang, could act as the two-dimensional surface encoding our 3D reality. Others suggest the principle might only apply to specific regions of spacetime, like black holes or the early universe. Yet the implications are staggering. If true, it would mean the solidity of the world around us is an illusion, a collective hallucination woven from quantum data. The holographic principle forces us to confront a profound question: Is reality just information? From the way black holes store data to the mathematical elegance of string theory, the universe seems to hint at a deeper, digital-like structure. Whether we're living in a hologram or not, the theory reshapes our search for a unified physics, not by adding new layers to reality, but by peeling them away. After all, if the cosmos is a projection, finding its source code might be the ultimate act of discovery, and that search could lead us to truths far stranger than we've ever imagined. Somewhere in the depths of the cosmos, hidden behind the dense veil of our own Milky Way, lurks something massive enough to bend the paths of entire galaxies toward it, yet we can't see it. This is the Great Attractor, a gravitational anomaly so powerful it's dragging thousands of galaxies, including our own, toward it at speeds exceeding 2 million kilometers per hour. The bizarre part, despite decades of searching, astronomers still don't fully understand what's causing this colossal pull. Some believe it's the largest concentration of matter in our local universe, while others suspect it might reveal a fundamental flaw in how we map the cosmos. The mystery begins with motion. In the 1970s, scientists noticed something odd. Galaxies in our cosmic neighborhood weren't just drifting apart due to the universe's expansion. They were also streaming toward a specific point in space, roughly 250 million light-years away in the direction of the constellation Centaurus. This motion defied expectations, hinting at a gravitational anchor far more massive than anything visible in that region. Early observations suggested a supercluster, a dense knot of galaxies and dark matter, but the math didn't add up. The observed mass couldn't explain the staggering pull. Then came an even stranger revelation: the Great Attractor might not be the final destination. Galaxies in its vicinity, including ours, seem to be part of a much larger flow, as if the attractor itself is being dragged toward something even more enormous. Enter Laniakea, a Hawaiian word meaning immeasurable heaven. In 2014, researchers mapped the motions of thousands of galaxies and identified this colossal supercluster, a cosmic filament 500 million light-years wide, with the Great Attractor sitting near its heart. Suddenly, the puzzle grew bigger. The attractor wasn't just pulling us, it was caught in a web of gravity binding countless galaxies together in a slow-motion dance. But not everyone's convinced. Skeptics argue that the Great Attractor's apparent pull could be an illusion, a side effect of how we measure cosmic velocities. Earth's motion orbiting the Sun, which orbits the Milky Way, which itself moves within the local group, creates a complex reference frame. Subtracting all these motions to isolate the peculiar velocity of our galaxy is like trying to calculate the speed of a passenger on a spinning carnival ride while standing on another spinning ride. If we've miscalculated any of these movements, the Great Attractor might be less a physical object and more a ghost in the equations. There's another tantalizing possibility: dark flow. Beyond Laniakea, astronomers have detected galaxies drifting toward a point even farther away, as if something beyond the observable universe is tugging at them. Could the Great Attractor be just one ripple in this vast, unseen current? The implications are dizzying. If true, it might mean our universe is lopsided on scales we can't yet comprehend, or that neighboring universes, if they exist, are exerting gravitational influence across cosmic boundaries. For now, the Great Attractor remains shrouded in dust literally. Our view of it is blocked by the Milky Way's zone of avoidance, a band of gas and stars so thick it obscures nearly 20% of the sky. New tools like infrared and radio telescopes are piercing this veil, revealing previously hidden galaxies and clusters. Each discovery brings us closer to understanding whether this cosmic anomaly is a definitive structure or a signpost pointing to deeper mysteries. One thing's certain: the universe doesn't give up its secrets easily, and in the case of the Great Attractor, the greatest revelation might still be waiting just beyond our line of sight. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of noise so powerful, so unusual, that the astronomer who discovered it circled the printout and scribbled, "Wow." In the margin, the signal's intensity and narrow frequency band matched exactly what scientists predicted an alien transmission might look like. For decades, it stood as the strongest candidate for extraterrestrial contact ever recorded until suddenly, it vanished, never repeating, leaving behind only questions and controversy. But what really caused the WOW signal? The debate divides into two camps: those who see it as a fleeting cosmic accident, and those convinced it was a deliberate message from the stars. First, the skeptics' favorite explanation, comets. In 2016, astronomer Antonio Perez proposed that two icy wanderers, 266P and 335P, might have been passing through the exact patch of sky the telescope was monitoring. Comets shed clouds of hydrogen as they near the Sun, and the WOW signal appeared at the frequency hydrogen naturally emits. The timing seemed plausible except for one glaring issue. No records confirm those comets were actually in the area that night. Critics argue the theory leans too heavily on coincidence, with no concrete evidence to anchor it. Then there's the artificial angle. The signal's frequency, in 420 MHz, sits in a quiet, protected band where earthly transmissions are banned, minimizing interference. It's the cosmic equivalent of a clear radio channel, perfect for broadcasting across the stars. Even more intriguing, the signal's intensity spiked and faded exactly as expected if it originated from a distant, rotating source, like a planet carrying a transmitter turning into and out of view. Some researchers suggest it could have been an interstellar beacon, a fleeting hello from a civilization briefly pointing their antenna our way, but why no repeat? If aliens were signaling, wouldn't they try again? Here's where the mystery deepens. The WOW signal appeared in a tiny slice of sky, narrower than the telescope's own field of view. To catch it, the sender would have needed to beam the transmission with laser-like precision directly at Earth, a feat implying they knew we were here. Yet if they had that knowledge, why only one burst? Perhaps the signal wasn't meant for us at all. Maybe it was interstellar leakage, a runaway communication or energy pulse from a distant civilization's technology, briefly crossing our path like a ship's spotlight sweeping over a foggy coast. New research adds another twist: the signal's structure. Recent analysis suggests it might have carried subtle patterns, hints of modulation that natural cosmic phenomena rarely produce. If true, it would bolster the case for an intelligent source, but skeptics counter that cosmic noise can mimic such patterns by pure chance. The debate rages on, fueled by the fact that we'll likely never know for sure unless the signal repeats. The WOW signal endures as a cosmic Rorschach test. To some, it's proof we're not alone; to others, a reminder of how easily nature can fool us. But perhaps its greatest legacy is the way it crystallizes the essence of the search for extraterrestrial intelligence, a field built on patience, ambiguity, and the unshakable belief that somewhere in the static, there might be a signal worth circling in red ink. After all, the universe is under no obligation to make itself easy to understand, but that won't stop us from listening. In October 2017, astronomers spotted something unprecedented: a strange, tumbling object hurtling through our solar system at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from interstellar space. But this wasn't just any wandering rock. Its bizarre properties, an elongated, cigar-like shape, an unusual brightness, and most perplexing of all, an unexplained acceleration as it raced away from the Sun, ignited fierce debate. Was it a natural oddity, or something far more extraordinary? The acceleration threw scientists for a loop. Comets speed up when sunlight vaporizes their ice, creating a glowing tail, but Oumuamua showed no such trail. Harvard astrophysicist Avi Loeb proposed a startling alternative. Maybe it wasn't a comet at all, but an artificial object, a solar sail propelled by starlight. These theoretical spacecraft, long dreamed of by astronomers, use ultra-thin reflective sheets to catch photons like wind in a cosmic sail. if Oumuamua was a discarded relic of alien technology, its acceleration would make eerie sense. The idea wasn't entirely fringe. Even NASA has experimented with solar sails, like the Light Sail project, but critics pounced, without direct evidence, calling it alien tech was, to many, a leap too far. Enter the hydrogen iceberg theory. Some researchers suggested Oumuamua might have been a frozen chunk of molecular hydrogen, a substance so fragile it vaporizes under sunlight without leaving visible dust. As it neared the sun, hidden hydrogen outgassing could have nudged it forward like a silent engine. The math almost worked except for one hitch. Molecular hydrogen ice is incredibly rare in the cold void of interstellar space. Forming an object as large as Oumuamua would require conditions no one's ever observed. Then came the nitrogen iceberg idea. Another team argued it could have been a splinter of a Pluto-like exoplanet, made mostly of solid nitrogen. As sunlight warmed its surface, nitrogen would sublimate, providing stealthy thrust. This explained the missing tail. Nitrogen gas is invisible to most telescopes. But again, problems arose. To survive its journey, Oumuamua would have needed to be nearly pure nitrogen, an unlikely scenario given how easily such a fragile structure should have shattered under cosmic radiation. The debate rages on because Oumuamua is gone streaking beyond our telescope's reach, leaving only tantalizing data. Was it a cosmic iceberg, a wandering shard of an alien world, or something more deliberate? The truth might remain forever out of reach, but the questions it forced us to ask are just as valuable, because whether natural or not, Oumuamua proved one thing: the universe is capable of surprises we're only beginning to imagine. And the next time an interstellar visitor arrives, we'll be watching much, much closer. Beyond Neptune's orbit, something massive is tugging at the icy debris of the Kuiper belt, and it shouldn't be there. Clusters of distant objects are tilted in eerily similar orbits, as if an unseen hand is hurting them. Some move backward against the solar system's flow, others angle sharply out of the ecliptic plane. The most compelling explanation: a hidden world, up to 10 times the mass of Earth, lurking in the frozen dark planet 9. The hunt for this phantom planet began with Anomalies. In 2016, astronomers Konstantin Batygin and Michael Brown noticed that 6 extreme Kuiper belt objects shared bizarre orbital alignments. Statistically, the odds of this happening by chance are less than 0.002%. It's like rolling dice and getting the same improbable number 6 times in a row. Something must be influencing the outcome. Computer simulations revealed that a distant, super-Earth-sized object could sculpt these orbits over millions of years, its gravity acting like an invisible leash. But why haven't we spotted it yet? The answer lies in the mind-bending vastness of the outer solar system. Planet 9, if it exists, could orbit up to 600 times farther from the Sun than Earth, so distant that sunlight takes weeks to reach it. At that range, even a giant world reflects almost no light, vanishing into the cosmic background like a black marble lost in a shadowy room. Compounding the challenge, its orbital period might span 10 to 20,000 years, meaning it's crawling through an unimaginably wide search area. Telescopes like Subaru and the Vera Rubin Observatory are scanning the skies, but it's akin to finding a single flickering candle in a continent-sized fog. Critics argue the evidence could be a fluke, a small sample illusion. Only a handful of these oddly aligned objects have been found, and observational biases might skew the data. Others propose alternatives: perhaps a grapefruit-sized primordial black hole, left over from the Big Bang, is warping orbits with its gravity, or maybe the collective pull of countless smaller objects, a dark disk of unseen icy bodies, mimics the effect of one large planet. Yet Planet 9's defenders counter with fresh clues. Some of the most distant Kuiper belt objects also tilt toward the Sun at the same angle, a pattern that's astronomically unlikely without a massive perturber. Even Sedna, the icy dwarf planet with its stretched, lonely orbit, fits the puzzle as if something snatched it from the inner solar system and flung it outward long ago. If real, Planet 9 would rewrite solar system history, it might be a rogue planet captured by the Sun's gravity, or a primordial giant ejected during Jupiter and Saturn's chaotic dance in the early solar system. Some theorists even speculate it could be the core of a failed gas giant, stripped of its atmosphere by some ancient catastrophe. Every undiscovered object in our cosmic backyard whispers the same tantalizing question: how well do we really know our own solar system? Until we find or rule out this elusive world, the mystery will keep pulling us deeper into the dark. In 1972, NASA Pioneer 10 spacecraft blasted off toward Jupiter, carrying humanity's first direct observations of the outer solar system. But decades later, scientists noticed something bizarre. Pioneer, along with its twin Pioneer 11, was slowing down more than physics predicted. This tiny but persistent deviation became known as the Pioneer Anomaly, a gravitational hiccup that defied explanation for over 30 years. At its peak, the deceleration measured just 8.74 times 10 to the minus 10 meters per second squared, roughly a billion times weaker than Earth's gravity. Yet this faint drag was enough to ignite a firestorm of debate. Was it a flaw in our understanding of motion, or a whisper of new physics lurking at the edges of known science? The leading explanation seemed mundane at first: thermal radiation. Pioneer's nuclear power source constantly emitted heat, and even the faintest photons bouncing off the spacecraft's dish-shaped antenna could impart a tiny recoil, like sunlight nudging a sunbather's skin. Early models suggested this thermal ping might account for most of the anomaly, but when engineers painstakingly reconstructed Pioneer's heat map, factoring in every watt radiating from its body and instruments, the numbers still didn't quite add up. The spacecraft was slowing down just a fraction more than thermal pressure alone could explain a discrepancy that left the door open for wilder possibilities. That's when theorists pounced. Could the anomaly hint at modifications to Einstein's general relativity? Some propose that gravity behaves slightly differently at extreme distances, a tweak that would reconcile the data without overthrowing physics. Others floated the idea of dark matter drag, that Pioneer was plowing through unseen particles clustered in the solar system, creating invisible friction. The most radical suggestion, a link to string theory's hidden dimensions, where gravity might leak into other realms, weakening its pull on our spacecraft over vast distances. The mystery deepened when other distant probes failed to show the same behavior. Voyager 1 and 2, despite venturing even farther than Pioneer, exhibited no such anomaly. Why would the effect target Pioneer alone? The answer lay in the spacecraft's design. Unlike Voyagers, which used thrusters to stabilize their orientation, Pioneers relied on spinning like a perfectly balanced top. This made them exquisitely sensitive to even the faintest external forces, turning them into accidental laboratories for testing physics in the cosmic quiet. Finally, in 2012, a breakthrough, a team analyzing decades of telemetry pinned the anomaly almost entirely on heat, not just from the power source, but from electrical components and even the decay of plutonium in its generators. The key was accounting for heat radiating unevenly across the spacecraft's surfaces, creating a subtle but measurable push. With this refined model, the anomaly vanished into the noise of measurement uncertainty. Case closed. Not entirely. A stubborn few percent of the deceleration still eludes absolute explanation, a reminder that even solved mysteries can leave tantalizing crumbs of doubt. The Pioneer anomaly's legacy isn't just about a spacecraft's odd behavior, it's a testament to science's obsessive precision. Researchers spent years chasing a force weaker than the weight of a snowflake on your palm, proving that sometimes the smallest deviations can lead to the biggest questions. And while most now agree thermal effects were the culprit, that unresolved sliver of uncertainty keeps the door cracked. After all, history shows us that today's accounting error might be tomorrow's revolution. For now, Pioneer's ghostly drag remains a masterclass in how hard the universe fights to keep its secrets. The cosmic microwave background, the afterglow of the Big Bang, should be the ultimate snapshot of randomness, a perfectly uniform sea of ancient light frozen in time. But when scientists mapped it in detail, they found something unsettling. Stretching across the heavens like a ghostly fingerprint, an eerie axis of alignment threads through the data, a pattern so statistically improbable it earned a name straight out of a conspiracy theory, the axis of evil. This isn't just a quirk in the numbers, it's a cosmic curveball that threatened to upend our most basic assumptions about the universe's birth. At first glance, the CMB looks like static tiny fluctuations in temperature, hotter and colder patches no larger than 1/100th of a degree. These wrinkles are supposed to be random, the scars of quantum jitters from the universe's first moments, but peel back the layers and anomalies emerge. The coldest and hottest spots aren't scattered chaotically, they line up along a single plane, almost as if the universe has a preferred direction. Even stranger, that axis eerily aligns with the plane of our solar system, a coincidence so staggering it defies odds of 1 in thousands. Scientists checked for errors, recalibrated instruments, even debated whether human bias had crept into the data. But the axis of evil refused to vanish, so what could explain it? One radical possibility: the universe isn't isotropic, the same in all directions, as the Big Bang theory assumes. Instead, it might have inherited structure from something before the Big Bang. Imagine a cosmic pendulum swinging through cycles of expansion and contraction, each bounce imprinting traces of the previous universe onto the next. The axis of evil could be one such scar, a gravitational memory etched into spacetime itself. Alternatively, it might hint at exotic physics, a primordial magnetic field woven into the fabric of the cosmos, or even the gravitational tug of a neighboring universe brushing against ours like a shadow. Skeptics argue the alignment could be a fluke, a trick of perspective akin to seeing faces in clouds. After all, the human brain is wired to find patterns, even where none exist. But the statistical weight is hard to dismiss. When the Planck satellite mapped the CMB with unprecedented precision, the anomaly persisted, whispering that our universe might be stranger and more structured than we ever imagined. The axis of evil forces a humbling question: are we seeing the universe as it truly is, or just through a keyhole, missing the vast architecture hidden beyond? Whether a cosmic coincidence or a clue to deeper truths, it reminds us that the universe rarely plays by the rules we set for it, and sometimes the most unsettling discoveries are the ones that point to everything we don't yet know. For decades, rumors have swirled about an ancient alien satellite, silently orbiting Earth, a mysterious object dubbed the Black Knight. Stories claim it's been watching us for 13,000 years, transmitting signals before vanishing without a trace. But peel back the layers of this cosmic conspiracy, and you'll find a tangled web of misinterpreted space debris, Cold War secrecy, and the human brain's uncanny knack for seeing patterns where none exist. The myth took root in the 1950s when newspapers reported that the U.S. military had detected an unidentified object in polar orbit, an impossible feat at the time, since no nation yet had the technology to launch satellites. Sensationalists leaped to conclusions: it had to be extraterrestrial, but the real explanation was far simpler. The echoes picked up by early radar were likely fragments of a Discoverer satellite, part of a classified reconnaissance program. These launches were so secretive that even the scientists tracking them often didn't know their purpose, fueling fertile ground for speculation. Then came the infamous space blanket incident. In 1998, astronauts aboard the Space Shuttle Endeavour spotted a dark, tumbling object during a mission later identified as a lost thermal blanket. But grainy footage and dramatic narration transformed mundane debris into proof of the Black Knight, with some even claiming its surface bore alien hieroglyphs. The truth, space missions shed equipment all the time. NASA estimates over 27,000 pieces of human-made junk currently orbit Earth, from discarded rocket stages to flecks of paint. But what about those eerie radio signals? In the 1920s, Norwegian engineer Jorgen Hals reported picking up strange delayed echoes, radio pulses bouncing back seconds after transmission, as if reflected by something unseen. Decades later, ufologists linked these anomalies to the Black Night. The reality, atmospheric phenomena like ionized gas clouds can create such echoes, and Hals himself never suggested an extraterrestrial origin. The legend's persistence reveals something deeper, our fascination with the idea we're not alone and that evidence might be hiding in plain sight. Psychologists call it epiphania, the tendency to find meaning in randomness, like seeing faces in clouds or hearing whispers in static. Combine that with the secrecy of early space programs, and you've got a recipe for myth-making. Yet the Black Knight's legacy isn't just about debunking. It's a testament to how easily the unknown becomes the supernatural, especially when cloaked in the vast, silent theater of space. Every unidentified flash or orbital glitch sparks new stories, because the cosmos, in its infinite mystery, will always leave room for wonder. And perhaps that's the real magic, not in ancient satellites, but in our endless hunger to believe there's more out there, waiting to be found. Stretching across a mind-numbing billion light-years, the Boots void isn't just empty, it's a cosmic nothingness so vast it defies logic. Picture this, a region of space nearly 7 times wider than the average distance between galaxies, yet containing almost nothing. No glittering spirals, no bright clusters, just a chilling expanse of near-perfect vacuum. Astronomers call it the Great Nothing, and its existence isn't just puzzling, it's statistically outrageous. According to our best models of cosmic structure, voids this big shouldn't exist. The odds of such a gap forming naturally, less than 1 in a million, so what ripped a hole in the universe? One spine-tingling possibility, quantum tunneling on a cosmic scale. In the subatomic world, particles can spontaneously tunnel through barriers they shouldn't classically penetrate, like an electron appearing on the wrong side of an uncrossable wall. Now stretch this phenomenon to universe-sized proportions. Some theorists suggest the Boots void might be the scar of a bubble of true vacuum, a pocket of spacetime where the fundamental forces briefly flickered into a more stable state, repelling matter in all directions like a cosmic airburst. If true, it would mean the void isn't empty, it's filled with a different kind of spacetime, one so alien it pushed the universe away. But there's a darker contender, the collision of universes. In the multiverse scenario, our cosmos might have slammed into another, leaving behind a bruise, a region where matter was violently ejected. Think of it like 2 soap bubbles merging, where they touch, the surface stretches thin. If another universe's physics differed even slightly, the aftermath could look eerily like the Boots void, a place where the rules of reality itself were overwritten. Skeptics argue it's just a freak accident, an unusually large fluctuation in the primordial density of the universe, frozen in time by expansion, yet even this explanation raises eyebrows. The void's edges are suspiciously sharp, and its shape isn't spherical but oddly elongated, like a fingerprint dragged across the cosmos. Could it be the imprint of something even stranger, like a black hole so ancient it predates the Big Bang, or the shadow of a higher dimensional object passing through our universe like a ship through fog? The Boots void forces us to confront an uncomfortable truth. Our maps of the cosmos might be missing entire chapters, whether a quantum anomaly, a multiverse crash site, or just a cosmic roll of the dice. Its silence echoes louder than any signal. And until we solve its riddle, it stands as a reminder the universe hides its greatest secrets in the places we least expect to look. For centuries, the moon's serene face has watched over Earth, its origins shrouded in mystery until 1974, when a radical idea shattered conventional wisdom. The giant impact hypothesis, now the leading theory, paints a violent and dramatic birth for our lunar companion. Picture this: early in Earth's history, a Mars-sized protoplanet named Theia, born from the same cosmic nursery as our world, veered off course and slammed into our young planet with cataclysmic force. The collision was so brutal it vaporized entire continents worth of rock, sending molten debris spiraling into orbit. Over time, gravity sculpted this wreckage into the moon we know today. The evidence, moon rocks brought back by Apollo astronauts, contain isotopes nearly identical to Earth's mantle, as if the two worlds share the same genetic blueprint. Computer simulations show the physics holds up. An oblique impact could eject enough material to form the moon while leaving Earth intact. Even the moon's oddly large size relative to Earth makes sense in this scenario. It's a cosmic detective story written in isotopes and gravity, but what if the moon didn't form from Earth's devastation? Enter the capture theory, a maverick idea suggesting the moon was a wandering orphan, snared by Earth's gravity as it drifted through the solar system. Proponents point to oddities like the moon's tilted orbit, which doesn't align neatly with Earth's equator, more consistent with a captured object than a co-formed one. Some moons in our solar system, like Neptune's Triton, are known captives, lending credibility to the idea. There's even a wild twist: if the early solar system was crowded with free-floating planetary embryos, as some models suggest, gravitational tugs could have slowed a passing moonlet just enough for Earth to grab it. The problem: chemistry. A captured moon would likely have a composition wildly different from Earth's, yet lunar samples mirror our planet too closely for pure chance. Unless, and here's where things get interesting, the moon formed near Earth in the first place, making capture less of a cosmic kidnapping and more of a homecoming. The debate isn't just academic, it's a window into Earth's own violent infancy. If Theia's impact is real, it means our planet's early years were a battlefield, with collisions shaping not just the moon but Earth's fate. The energy from that crash could have melted the young planet's surface, resetting the clock for life's emergence. On the other hand, if the moon was captured, it implies a gentler origin, a celestial dance of gravity and chance. There's even a middle ground, perhaps a hybrid scenario where a smaller impact still ejected debris, and the moon formed partly from Earth's material and partly from a captured interloper. New missions might tip the scales. Future lunar samples, especially from the moon's elusive far side, could reveal isotopes or minerals that break the tie. Until then, the moon keeps its secrets, a silent witness to the chaos or serendipity that birthed it. One thing's certain: whether forged in fire or found by fate, our moon is more than a pretty face in the night sky. It's a time capsule from Earth's wildest days, and unlocking its past might just reveal our own. Imagine a star so bizarre that astronomers briefly considered the possibility it was surrounded by an alien megastructure. Meet KZ8462852, better known as Tabby's star, named after astrophysicist Tabitha Boyajian, who first uncovered its strangeness. This unassuming star, roughly 500 light-years away, behaves like nothing else in our galaxy. Over periods of days or weeks, its light dims erratically, sometimes plunging by a staggering 22%, far more than any known planet could cause. These dramatic drops aren't regular or predictable, as if something massive and irregular is passing in front of it, but what could possibly blot out a star's light to such an extreme degree? The most sensational explanation, and the one that captured headlines, was the Dyson swarm hypothesis. If an advanced civilization had built a vast array of solar collectors around the star to harness its energy, these structures could intermittently block its light as they orbit. The idea wasn't entirely far-fetched. Physicist Freeman Dyson had theorized decades earlier that sufficiently advanced societies might build such megastructures to meet their energy demands. The dips in Tabby's star's brightness seem to fit a swarm, still under construction, might explain the irregular patterns, scientists even scoured the star's radio emissions for signs of artificial signals, though none were found. But nature often trumps speculation. Further observations revealed a crucial clue: the star dimmed more in blue light than in red, a telltale sign of dust scattering. Unlike solid megastructures which would block all wavelengths equally, fine particles preferentially scatter shorter wavelengths. This pointed to a more mundane culprit: vast clouds of cosmic dust, possibly from a recent planetary collision or a swarm of disintegrating comets. In 2018, the star's most dramatic dimming event yet was monitored in real time, and the data confirmed it. Dust, not alien engineering, was to blame. Yet the mystery only deepened. Where did this dust come from? Ordinary star systems don't produce such erratic, deep dimming events. Some theorists propose a belts of objects theory, a dense, clumpy ring of debris, possibly shaped by an invisible planet's gravity, casting uneven shadows. Others suggest the star itself is unstable, undergoing rare stellar convulsions that eject immense plumes of dust. There's even a wildcard idea: a vaporized exomoon, torn apart by tidal forces and now spreading its remains across the star's orbit. Tabby's star may not host aliens, but its true story is no less fascinating. It challenges our assumptions about how star systems evolve and how strange cosmic phenomena can mimic our wildest sci-fi dreams. Whether it's a graveyard of shattered worlds or a celestial mystery still unfolding, this star reminds us the universe loves a good plot twist, and sometimes, the truth is stranger than anything we could invent. Buried within the cosmic microwave background, the universe's oldest light lies a chilling anomaly that defies explanation: the CMB cold spot. Stretching across a vast region of space, this eerie patch is colder than its surroundings by a margin that shouldn't exist according to standard cosmology. Statistically, the odds of such a deviation occurring by chance are less than 1 in 50, so what could have left this cosmic bruise? One daring explanation suggests it's not a flaw in the data, but a fingerprint, one left by a collision with another universe. The cold spot isn't just a minor temperature dip, it's a colossal void, spanning nearly 200 million light-years, where the universe seems oddly empty. Normally, such voids explain cooler regions. Less matter means less gravitational pull, so light passing through loses energy, a phenomenon called the integrated Sachs-Wolf effect. But the cold spot's temperature drop is too extreme for even the largest known voids. Simulations show it's like finding a freezer in the middle of a desert. The numbers just don't add up. Unless, of course, something far stranger is at play. Enter the multiverse hypothesis. In some models of eternal inflation, our universe isn't alone. It's one bubble in a frothing sea of universes, each with its own physics. If another bubble brushed against ours in the distant past, the energy release could have pushed matter away, leaving behind a vast, underdense region. The cold spot in this view would be the cosmic equivalent of a dent in a car fender, evidence of a fender bender with a parallel reality. The idea isn't as outlandish as it sounds. Quantum field theory allows for such collisions, and if they happened, the cold spot's peculiar properties fit the expected aftermath, but skeptics aren't convinced. Some argue the cold spot could be a statistical fluke, a cosmic illusion amplified by the way we map the CMB's fuzzy data. Others propose less exotic explanations, like a supervoid, a sprawling region of sparse galaxies whose gravity subtly distorts the CMB. Yet even supervoids struggle to account for the cold spot's severity. The most intriguing counterpoint, the spot's polarization patterns. If it were a true void, the light's polarization would follow certain rules, but preliminary studies suggest deviations, as if the spot's origins are more complex than mere emptiness. The stakes are high. If the cold spot is proof of a multiverse, it would revolutionize our understanding of reality, confirming that our cosmos is just one page in an infinite library of universes. Future telescopes like the Simons Observatory aim to scrutinize the spot's fine details, hunting for telltale signs of a collision, perhaps imprints of exotic particles or gravitational waves frozen in time. Until then, the cold spot remains a tantalizing riddle, a whisper from the edge of physics where the known and the unimaginable blur. Whether a cosmic accident or a window into the multiverse, it challenges us to reconsider just how strange the universe might truly be. Galaxies aren't just drifting apart in the expanding universe, some are being pulled towards something vast and invisible in the distant darkness. Astronomers call this phenomenon the dark flow, a mysterious current where clusters of galaxies stream in the same direction at speeds over 2 million miles per hour, as if drawn by an unimaginable force beyond the cosmic horizon. The strangest part, there's nothing there, at least, nothing we can see. This isn't just a few galaxies out of step, it's a coordinated movement spanning billions of light years, defying the smooth, uniform expansion we expect from the Big Bang's aftermath. What could possibly exert such gravitational influence from outside our observable universe? The leading theory is as mind-bending as it sounds. The dark flow might be the tug of another universe. In multiverse models, our cosmos could be one bubble among countless others, each with its own physical laws. If a neighboring universe passed close enough in the past, its gravity might have left a lingering imprint, dragging matter toward it like an invisible riptide. Picture two soap bubbles floating in a sink where they nearly touch, their surfaces stretch and warp. If our universe brushed against another, the gravitational distortion could still be steering galaxies billions of years later. The math supports it. Simulations show such collisions could create coherent flows on scales matching the dark flow's eerie alignment, but skeptics aren't ready to jump to multiverses just yet. One alternative suggests the flow is an illusion, a quirk of how we measure cosmic motion. Our solar system isn't stationary, it's hurtling through space as part of the Milky Way's own journey. Subtracting all these overlapping movements to isolate the true, peculiar velocity of distant galaxy clusters is like trying to calculate the speed of a swimmer in choppy seas while standing on a moving boat. Any miscalibration could artificially amplify the apparent flow, yet even after accounting for these effects, the dark flow persists, its signal too strong to dismiss as noise. Then there's the matter of scale. The dark flow's coherence across such vast distances suggests a source of staggering mass, perhaps a supercluster trillions of light years away, or a cosmic defect left over from the universe's birth. Some theorists propose it could be a cosmic texture, a hypothetical wrinkle in spacetime formed during the Big Bang's chaotic early moments. These defects would warp gravity on colossal scales, creating phantom attractors where none should exist. Others wonder if dark energy, the force accelerating cosmic expansion, isn't uniform after all, but varies in ways that nudge galaxies en masse toward unseen overdensities. The most tantalizing clue, the dark flow aligns roughly with the CMB's axis of evil, that cryptic pattern in the cosmic microwave background that also hints at a directional anomaly in the universe. If both phenomena trace back to the same primordial disturbance, a multiversal collision, a gravitational echo from before the Big Bang, it could mean our cosmos is far less isotropic than we've assumed. Future galaxy surveys and precision measurements of the CMB might finally settle the debate, revealing whether the dark flow is a shadow from another reality or just a cosmic trick of the light. Until then, it stands as one of the most haunting mysteries in cosmology, the unsettling possibility that something out there, beyond the edge of everything we know, is pulling us into the dark. The first grainy images from Mars in 1976 should have been just another set of planetary snapshots, until one frame sent conspiracy theorists into overdrive. Nestled in the Cydonia region, a mesa bore an uncanny resemblance to a human face staring blankly into space, complete with shadowed eye sockets and what looked like a faint smile. NASA scientists dismissed it as a trick of light and angle, but the face on Mars, became an icon of extraterrestrial speculation, fueling claims of ancient civilizations and cover-ups. Decades later, high-resolution scans revealed the truth. The face was just a weathered hill, its haunting features smoothed into ordinary geology by better cameras. Yet this story isn't just about optical illusions, it's about how desperately we want Mars to whisper back to us, even when it's just the wind carving rocks. But pareidolia, our brain's tendency to find familiar shapes in randomness, doesn't explain everything puzzling about the red planet. Take the so-called pyramids of Elysium Planitia. These angular structures, photographed by rovers, appear eerily symmetrical, with edges too sharp for typical erosion. Mainstream science attributes them to volcanic basalt fracturing into geometric blocks, a common geological process. Yet the precision nags at the imagination. On Earth, similar formations like the Giant's Causeway form naturally, but Mars lacks the tectonic activity to neatly split rock on such a scale. Could these be eroded remnants of something artificial? The odds are vanishingly slim, but the mystery lingers in the way these structures refuse to fit neatly into textbook explanations. Then there's methane, a gas that shouldn't exist in Mars' thin atmosphere unless something is actively producing it. On Earth, 90% of methane comes from living organisms, from cows to microbes. When NASA Curiosity rover detected sporadic methane spikes in Gale crater, the scientific community split. Some pointed to geological sources, like serpentinization, a mineral reaction that releases methane, or ancient gas seeping from underground reservoirs. But the timing is suspicious. The spikes appear seasonally, like clockwork, as if something beneath the surface is breathing. Even more intriguing, the European Space Agency's Trace gas orbiter, designed specifically to sniff out methane, often finds none at all, creating a maddening discrepancy. Either Martian methane vanishes faster than physics allows, or our instruments are missing a crucial piece of the puzzle, the most tantalizing thread weaving these anomalies together. Mars wasn't always the barren wasteland we see today. Billions of years ago it had rivers, lakes, even a vast ocean. If life ever took root there, even microbial, it might have left behind subtle traces we're only now learning to decode. The Viking landers in the 1970s conducted experiments that some scientists still argue detected microbial metabolism, though most dismiss the results as chemical quirks of Martian soil. Modern rovers like Perseverance are hunting for biosignatures, complex molecules, or textures only life could create. The stakes couldn't be higher. Finding even fossils on Mars would prove life isn't a fluke of Earth, but a cosmic inevitability. So are the face, the pyramids, and methane proof of Martians? Almost certainly not, but there's something equally valuable, a reminder that Mars remains a world of unanswered questions, where the line between geology and biology blurs. Every anomaly, whether debunked or unexplained, tightens the knot of curiosity, because if we ever do find life there, it likely won't be a statue or a pyramid, it'll be a whisper in the chemistry of a rock, a pattern in the data, waiting for us to listen closely enough. And until then, the red planet will keep teasing us with riddles, knowing we can't resist trying to solve them. Venus has always been the solar system's enigma, a hellish world shrouded in thick, acidic clouds where surface temperatures melt lead. But in 2020, this toxic paradise became the center of a cosmic controversy when astronomers announced they detected phosphine gas in its atmosphere. On Earth, phosphine is almost exclusively produced by life anaerobic microbes thriving in oxygen-free environments like swamps and animal guts. Finding it on Venus was like smelling a barbecue on a lifeless desert island, utterly unexpected and begging for an explanation. The discovery ignited a firestorm of debate. Was this our first whiff of extraterrestrial life, or just a quirk of chemistry in one of the most hostile places imaginable? The initial detection came from two independent telescopes, the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. Both picked up phosphene's spectral fingerprint at concentrations of around 20 parts per billion, far higher than non-biological processes should produce. The team behind the study meticulously ruled out known abiotic sources, meteorites, lightning, even volcanic eruptions. Their conclusion: either we're missing something fundamental about Venusian chemistry, or we're seeing the metabolic byproducts of floating microbes. The idea isn't as wild as it sounds. 50 kilometers above Venus' scorching surface, the cloud decks are surprisingly temperate, with pressures similar to Earth's and droplets of water mixed with sulfuric acid. Some extremophiles on Earth thrive in similar conditions, leading to speculation that Venus clouds could harbor aerial life, organisms riding the winds like cosmic plankton. But skepticism erupted almost immediately. One major objection: the sheer difficulty of detecting phosphine at all. Venus' atmosphere is a thick soup of sulfur dioxide, which can mimic phosphine signal in certain wavelengths. Critics argue the team might have misread the noise, picking out a phantom signal from the cosmic static. Others pointed to unknown geological processes. Venus is riddled with volcanoes, and while Earth's eruptions don't produce much phosphine, Venus' extreme chemistry might cook it up in unexpected ways. There's even a wild card theory involving solar wind slamming into Venusian dust, creating exotic phosphorus compounds that degrade into phosphine over time. The plot thickened when follow-up observations failed to consistently reproduce the result. Some teams found hints of phosphine, others found nothing. The European Space Agency's Venus Express orbiter, which studied the planet for 8 years, had data that could have settled the debate, but its instruments weren't tuned to spot phosphine specifically. It's like having a security camera that only catches glimpses of a shadow. You can't tell if it's a burglar or a tree branch. This uncertainty fueled accusations of premature hype, with some scientists arguing the original team jumped too eagerly to biological explanations. Yet the phosphine mystery refuses to die quietly. In 2021, a reanalysis of archival data from NASA Pioneer Venus mission, a spacecraft that dropped probes into the clouds in 1978, revealed traces of phosphorus compounds that could be phosphine precursors. Even more intriguing, Venus' atmosphere has another unexplained anomaly: patches of UV-absorbing particles that behave almost like algal blooms on Earth. Could these be the very organisms churning out phosphine as they drift through the acidic haze? The debate epitomizes the razor's edge of astrobiology. Extraordinary claims demand extraordinary evidence. If phosphine is truly there, and truly biological, it would mean life isn't confined to Earth's cozy Goldilocks zone. It can thrive in the most acidic, inhospitable corners of the cosmos. But if it's just a misunderstood chemical quirk, Venus becomes a cautionary tale about reading too much into ambiguous data. Upcoming missions like NASA Da Vinci and ESA Envision aim to settle the score by directly sampling Venus' atmosphere and mapping its chemistry in unprecedented detail. Until then, the phosphine debate remains a tantalizing reminder sometimes the universe's biggest mysteries aren't in the distant stars, but right next door, hidden in plain sight. Deep in the outer reaches of our solar system, something might be lurking, an ancient cosmic predator silently shaping Earth's darkest chapters. This is the Nemesis hypothesis, a theory proposing our Sun has a hidden companion, a dim, icy dwarf star locked in a sprawling orbit so vast it takes 26 million years to complete a single lap around our solar system. But Nemesis isn't just a passive neighbor. Every time it swings closest to the Sun, its gravity stirs up comets in the distant Oumuamua cloud, hurling them inward like a celestial cue ball breaking a rack. Some of these icy missiles would inevitably strike Earth, and, if the timing aligns with mass extinctions in our planet's fossil record, it could explain why life keeps getting reset in brutal cycles of fire and ice. The idea first gained traction in the 1980s, when paleontologists noticed a chilling pattern. Earth's major extinction events, like the one that wiped out the dinosaurs, seem to occur roughly every 26 to 30 million years. Meanwhile, astronomers knew the Oort cloud, a vast shell of icy debris surrounding our solar system, held trillions of comets primed for disruption. The connection was irresistible. Could a distant object, unseen but massive enough to perturb these comets, be the cosmic executioner behind these die-offs? Enter Nemesis, a hypothetical red or brown dwarf star, faint and cold enough to evade detection, yet gravitationally potent enough to rewrite our planet's fate with each distant passage. Evidence for Nemesis is frustratingly indirect but tantalizing. The extinction periodicity isn't perfect, but it's statistically notable, like finding a series of bullet holes lining up suspiciously at a crime scene. Then there's the peculiar orbits of some extreme trans-Neptunian objects, which cluster in ways suggesting an unseen mass warping their paths. Could this be Nemesis' fingerprint? The math suggests we need an object roughly the size of Jupiter to create such disturbances, but stars like Nemesis could easily fit the bill. The challenge is spotting it. Brown dwarfs emit almost no visible light, glowing faintly in infrared. Even our most powerful telescopes might miss one unless we knew precisely where to look, and with an orbit stretching a quarter of the way to the nearest star, precise is a cosmic needle in a haystack. Critics argue that improved extinction records have mudded the 26-million-year cycle, with some events falling out of sync. Others point out that galactic tides, the gentle gravitational pull from the Milky Way's disk, could perturb the Oort cloud just as effectively as a hidden star. And then there's the silence of infrared surveys. Missions like WISE, the Wide Field Infrared Survey Explorer, have scanned the skies for cold dwarf stars, turning up candidates but nothing matching Nemesis' predicted mass or trajectory. Yet the theory refuses to die. Some researchers propose Nemesis might not be a star at all, but a rogue planet, a super-Earth ejected from another system, now drifting unseen in the frigid dark. Others suggest it could have been flung away by a passing star long ago, its influence frozen in time like a gunshot's echo, the most tantalizing twist. If Nemesis exists, we might not need to see it to confirm it. Upcoming observatories like the Vera Rubin telescope could spot the subtle warping of distant comet orbits, tracing the invisible hand of a cosmic puppeteer. Until then, Nemesis remains the ultimate ghost story, a shadowy figure written into the scars of Earth's past, waiting silently for its next act. Empty space isn't really empty, it's a seething quantum foam, alive with particles blinking in and out of existence so fast we can barely fathom it. This frenzy of activity should generate an unfathomable amount of energy, flooding the vacuum of space with enough power to rip the universe apart. Yet when we measure the actual energy of the vacuum, it's almost zero, so close to nothing that the mismatch between prediction and reality spans a staggering 120 orders of magnitude. That's like calculating the weight of a mountain and finding a single grain of sand on the scale instead. This cosmic accounting error is known as the quantum vacuum catastrophe, and it's not just a minor glitch, it's the largest discrepancy in all of science, pointing to a gaping hole in our understanding of reality. Where does this phantom energy come from? Quantum field theory tells us that even in a perfect vacuum, pairs of virtual particles constantly pop into existence, borrowing energy from nowhere before annihilating each other in fractions of a nanosecond. This dance, known as quantum fluctuations, should generate an overwhelming energy density, enough to curve space-time so violently that stars and galaxies couldn't form. The math is airtight, but the universe stubbornly refuses to comply. Cosmologists call this the cosmological constant problem. Einstein's fudge factor for the energy of empty space, which he later called his greatest blunder, turns out to be absurdly tiny compared to what quantum mechanics demands. So why doesn't the vacuum explode with energy? One unsettling possibility: we're missing something fundamental about how gravity interacts with the quantum realm. At subatomic scales, gravity is so weak it's practically irrelevant, and no theory yet unifies it seamlessly with quantum mechanics. Perhaps some unknown mechanism cancels out the vacuum's energy almost perfectly, like a cosmic balancing act where positive and negative contributions mysteriously negate each other. String theory offers a speculative fix, suggesting extra dimensions might leak away the excess energy like water draining through hidden cracks, but there's a darker alternative. What if the vacuum energy hasn't cancelled out completely? The tiny residual we detect today, driving the universe's accelerated expansion, might be the leftover drip of an incomplete cancellation. If so, we're living on borrowed time. Vacuum energy isn't static. Quantum fields can shift states, tunneling into lower energy configurations. If that happened, the vacuum could suddenly rewrite its own rules, unleashing a big slurp that resets the laws of physics in a propagating wave of annihilation. One moment atoms hold together, the next they dissolve into a new, alien reality. The quantum vacuum catastrophe forces us to confront an unnerving truth. Our most elegant theories might be grotesquely wrong, or we're blind to some deeper symmetry governing the cosmos. Solving it won't just reconcile quantum mechanics and gravity, it'll reveal whether the universe is finely tuned for life, or if we're just temporary guests in a house built on a foundation we don't yet understand. Until then, every measurement of empty space whispers the same terrifying question: what if the void isn't empty at all, but coiled with energy waiting to wake? Imagine waking up one day with all your memories intact only to realize you might not actually exist. This is the unsettling heart of the Boltzmann brain paradox, a thought experiment so bizarre it forces us to question whether our entire existence could be a fleeting accident in an infinite sea of chaos. The idea springs from thermodynamics, specifically the work of physicist Ludwig Boltzmann, who recognized that even in a universe tending toward disorder, random fluctuations can briefly create pockets of order. Given enough time, these fluctuations could theoretically assemble a fully conscious, self-aware mind, a Boltzmann brain, out of pure randomness, complete with false memories of a past that never happened. At first glance, the notion seems absurd, but consider the numbers. In an infinitely old or infinitely vast universe, every possible configuration of particles, no matter how improbable, must eventually occur. The odds of atoms randomly arranging themselves into a functioning brain are astronomically low, but infinity means even the impossible becomes inevitable. If Boltzmann brains can pop into existence, statistically there should be vastly more of them than real brains like ours, evolved through natural processes. Which raises a terrifying question: how do you prove you're not one? Critics argue the paradox relies on faulty assumptions. Our universe isn't static and eternal. It had a beginning with the Big Bang, imposing limits on how long such fluctuations could play out. Quantum field theory also suggests true vacuums are stable, preventing the kind of large-scale fluctuations needed to spawn Boltzmann brains spontaneously. Yet defenders counter that even our understanding of cosmic inflation allows for pockets of false vacuum where anything might emerge, given enough time. The real sting of the paradox isn't just metaphysical, it undermines science itself. If most conscious experiences are Boltzmann hallucinations, then our observations about the universe's laws become untrustworthy. The consistency of physics, the apparent fine-tuning for life, even the reliability of memory, all crumble under the weight of statistical doubt. Some physicists, like Sean Carroll, propose the paradox as a reductio ad absurdum, revealing flaws in how we model infinity or probability. Others lean on the anthropic principle. The fact we're having this debate at all suggests we're likely real, since Boltzmann brains would dissolve back into chaos before constructing coherent thoughts. But the debate refuses to die. Modern cosmology's embrace of the multiverse, where countless universes bubble into existence with random properties, reignites the paradox. In an endless froth of realities, Boltzmann brains might dominate unless some deeper principle prevents them. Perhaps consciousness requires not just ordered particles, but continuous interaction with an external world, making isolated brains impossible. Or maybe reality itself is a kind of stable hallucination, a shared illusion woven from quantum entanglement. Ultimately, the Boltzmann brain paradox is less about brains than boundaries, how far we can trust logic when stretched to cosmic extremes. It's a mirror held up to our deepest anxieties about existence, randomness, and meaning. Whether a thought experiment or a genuine crisis for physics, it forces us to confront an unnerving truth. In a universe vast enough, even the most impossible things might be inevitable. And that uncertainty in itself is a kind of madness. Black holes aren't just cosmic vacuum cleaners. What if they're also cosmic wombs? The black hole universe theory flips everything we thought we knew on its head, proposing that our entire universe isn't expanding from a singularity, but into one. Imagine the Big Bang not as an explosion in empty space, but as the moment a dying star collapsed into a black hole in some higher dimensional reality. The singularity at its core, that's our Big Bang, and the event horizon we call the observable universe, is the boundary we can never cross. It's a mind-bending twist that could solve some of cosmology's biggest riddles, if we dare to follow the logic. Start with the numbers. A black hole's entropy, a measure of its hidden information, is proportional to its surface area, not its volume. Our universe, oddly enough, follows the same rule. The cosmic horizon, the farthest light we can see, behaves mathematically like a black hole's event horizon, with the universe's total information seemingly encoded on its boundary. Even stranger, the universe's expansion accelerates, just like matter falling toward a singularity speeds up as it approaches. Coincidence or cosmic design? This isn't just poetic symmetry. The theory could explain dark energy, the mysterious force driving cosmic expansion. In a black hole universe, dark energy might be the gravitational pull of the singularity we're all falling toward. It's like being inside a collapsing star, where every point in space is rushing toward the center, creating the illusion of expansion. Even the universe's eerie uniformity makes sense. The cosmic inflation after the Big Bang could be the smoothing effect of a black hole's violent birth, stretching spacetime into equilibrium. But how would this even work? Enter the holographic principle, the idea that our 3D reality is a projection of information stored on a 2D surface. If we're inside a black hole, the universe's boundary could be the true source code, with everything we experience, galaxies, consciousness, even time, rendered from data on that distant horizon. Picture a movie screen where the images have depth, but the pixels are flat. Our reality might be the same, an immersive illusion built from simpler, flat mathematics. Critics raise obvious objections. If we're inside a black hole, why don't we see crushing tidal forces or a visible singularity? The answer lies in scale. A universe-sized black hole would have such gentle curvature that its interior would feel nearly flat, just like our cosmos. As for the singularity, it's not a point in space, but everywhere in our past, the Big Bang itself, the moment the black hole formed in the parent universe. The wildest implication, our black hole universe could be nested inside another, like a cosmic Russian doll. Every black hole in our cosmos might contain its own universe, each with its own laws, stars, and perhaps even life. It's a fractal vision of reality, where creation isn't a one-time event but an endless cascade. And if that's true, the ultimate question isn't, what came before the Big Bang? It's what universe birthed ours. The black hole universe theory blurs the line between destruction and creation, suggesting that every cosmic ending might seed a new beginning. Whether it holds up or not, it forces us to rethink the most basic questions: where we are, how we got here, and what might lie beyond the event horizon of our understanding. After all, if the universe is a black hole, then the greatest mysteries aren't out there in the stars, they're written in the very fabric of our existence. What if time itself could crystallize, not in metaphor but as a tangible, repeating structure built into the fabric of reality? This is the extraordinary premise behind time crystals, a bizarre new phase of matter that defies everything we thought we knew about equilibrium. Unlike ordinary crystals like diamonds or snowflakes, where atoms arrange themselves in repeating patterns in space, time crystals oscillate in time, locking into rhythms that persist without energy input. Picture a clock that ticks forever without winding, or a dance of particles that never loses its rhythm, even in the deepest vacuum of space, first proposed in 2012 and experimentally confirmed just 5 years later. These structures aren't just laboratory curiosities, they might hold the key to understanding cosmic cycles far grander than we've ever imagined. At their core, time crystals break one of physics' most sacred rules, the symmetry of time. Normally, the laws of physics don't care if you run the clock forward or backward, but time crystals refuse to play along. Their components, whether ions, spins of electrons, or even light particles, flip between states at fixed intervals, creating a self-sustaining loop that's immune to entropy's decay. It's like finding a pendulum that swings forever without friction, not because it's perfectly engineered, but because the universe itself forces it to keep time. In 2017, researchers created the first time crystal by trapping ytterbium atoms in a laser grid and nudging them into motion. Shockingly, the atoms kept flipping their spins rhythmically long after the initial nudge, as if trapped in a quantum metronome. Now scale this up to cosmic proportions. Some theorists propose that space-time itself might harbor primordial time crystal structures forged in the Big Bang's fury, imprinting oscillations on the universe's very fabric. These wouldn't be tiny lab artifacts, but vast, invisible lattices governing the ebb and flow of cosmic epochs. Imagine a universe where expansion and contraction aren't random, but dictated by a deeper, crystalline tempo, like a heartbeat woven into existence. It's a radical twist on cyclic cosmology, suggesting the Big Bang might not have been a one-time event but a single pulse in an endless cosmic rhythm. Even more mind-bending, time crystals could explain quantum entanglement's spooky link between particles. If entangled particles are connected through microscopic time loops, tiny crystals vibrating in sync across space, their instantaneous coordination stops seeming so mysterious. It's as if the universe has hidden gears, meshing together beneath the surface of reality. Recent experiments with quantum processors hint at this possibility, showing entangled qubits settling into time crystal-like synchronization without direct interaction. The implications spiral outward. If time crystals permeate the vacuum of space, they might subtly influence everything from dark matter's distribution to the universe's expansion rate. Some models even suggest they could act as cosmic memory, preserving information from previous cycles in their immutable patterns. It's a haunting thought. The universe might not just have a history, it could be built from it, layer upon layer like geological strata in a mountain of time. Yet for all their promise, time crystals raise thorny questions. How could such structures emerge naturally? Most known examples require precise conditions to avoid collapsing into chaos. And if they're so pervasive, why haven't we detected their fingerprints in cosmological data? The answers might lie in the quantum realm's fuzziness, where time crystals could exist as fleeting, probabilistic phenomena, flickering in and out like fireflies in the dark. Whether cosmic or quantum, time crystals challenge our most basic assumptions about reality's architecture. They suggest that time isn't just a backdrop, it's an active participant, with structures as real as galaxies or atoms. And if we're right about their role, the universe might be less like a machine and more like a grand, self-sustaining song, its rhythm echoing across eternity. Right now, dark energy is the universe's quiet architect, steadily stretching the cosmos apart, driving galaxies away from each other faster and faster. But what if this mysterious force isn't just a passive backdrop? What if it's a cosmic time bomb, growing stronger until it shreds reality itself? This is the nightmare scenario known as the Big Rip, a theory so violent it makes black holes look gentle. Imagine dark energy not as a steady pressure, but as a runaway train, accelerating until it overwhelms gravity, then electromagnetism, then even the nuclear bonds holding atoms together. First, galaxies would vanish over the horizon of space, ripped from view, then stars would dissolve as their light can't outpace the swelling void, planets would splinter into dust, molecules torn mid-formation. In the final moment, spacetime itself would fracture, atoms exploding into disconnected particles, reality dissolving into a sea of lonely quarks drifting in the dark. The math behind this apocalypse hinges on dark energy's equation of state, a measure of how its density changes over time. If it remains constant, the universe expands forever but never tears apart. But if dark energy strengthens, labeled as phantom energy, it could reach infinite density in finite time. Think of it like compound interest on a loan where the interest rate grows faster than your payments eventually. The debt becomes unstoppable. In cosmic terms, this means phantom energy's grip would tighten exponentially, amplifying expansion until it overpowers every force we know. The countdown. Perhaps as little as 22 billion years from now, a blink in cosmic time. Critics argue the Big Rip relies on speculative physics. Phantom energy violates the null energy condition, a foundational rule that says energy densities shouldn't become negative. Yet quantum field theory allows for such violations in fleeting, microscopic bursts. Could dark energy somehow exploit this loophole on a universal scale? Some models suggest it might, especially if dark energy isn't a uniform field but a dynamic fluid with evolving properties. Others propose the rip isn't an end but a transformation, a phase transition where space-time cracks into new dimensions, birthing a fresh universe with different laws. The scariest part, we're flying blind. Current tools can't measure dark energy's equation of state precisely enough to rule out phantom behavior. Upcoming projects like the Dark Energy Spectroscopic Instrument aim to tighten the constraints, hunting for clues in the distribution of galaxies across billions of light years. If they find even a hint that dark energy is strengthening, the clock starts ticking not just for stars and planets, but for the fabric of existence itself. Yet amid the doom, the Big Rip offers a perverse sort of hope. If the universe can end so violently, it might mean our understanding of physics is incomplete, that deeper laws await discovery. After all, nature rarely lets infinities manifest without a catch. Whether a flaw in our models or a genuine cosmic death sentence, the Big Rip forces us to confront a humbling truth: the universe's fate isn't written in stone. It's woven into the dark, and we've only just begun to read the pattern. What if the universe exists because you're looking at it? This isn't just existential navel-gazing, it's the radical core of the consciousness-created cosmos theory, where quantum mechanics and philosophy collide in a way that reshapes reality itself. The idea stems from one of quantum physics' most baffling behaviors. Particles don't settle into definite states until they're observed. In the infamous double-slit experiment, electrons behave as waves when no one's watching, fanning out in probabilistic clouds. But the moment a detector clicks on, they snap into sharp, localized points like well-behaved particles. It's as if the universe is waiting for an audience before deciding what's real. This observer effect isn't just about clumsy instruments disturbing delicate systems. At the quantum level, observation seems to create reality. Take Schrödinger's cat, the thought experiment where a feline in a box hangs in limbo, simultaneously alive and dead until someone peers inside. Most dismiss it as a metaphor, but some theorists argue it's literal. No outcome exists until consciousness forces the quantum dice to land. Extend this to the cosmos, and you're left with a staggering possibility: the Big Bang, galaxies, even the chair you're sitting on might only crystallize into existence because minds like yours are here to witness them. The implications spiral into metaphysics. If consciousness shapes reality, what does that mean for the universe before life evolved? One interpretation: the cosmos retroactively bootstrapped itself into being once observers emerged, like a movie rendering scenes only when the audience arrives. This participatory universe idea, championed by physicist John Wheeler, suggests that human perception isn't a passive byproduct of cosmic evolution, it's the very mechanism that completes it. In this view, the fine-tuning of physical constants isn't luck, it's inevitability. Only a universe capable of birthing observers could ever become definite, because observation is the missing ingredient that collapses quantum possibilities into concrete history. Critics counter that this veers into solipsism, reducing the universe to a collective hallucination. They point out that quantum decoherence interactions with the environment can explain wave function collapse without invoking consciousness. A stray photon bouncing off an atom serves as an observer just as well as a human brain, but proponents fire back: what exactly qualifies as an observer? Rocks and cameras don't experience qualia, the raw feeling of existence. Perhaps only true consciousness, with its capacity for meaning, can stitch reality together from the quantum fog. The wildest twist: this theory might bridge science and spirituality. Buddhist philosophy has long posited that reality is inseparable from perception, while quantum pioneers like Niels Bohr hung the slogan, "No phenomenon is a phenomenon until it is an observed phenomenon," in his office. Even modern neuroscience reveals that our brains don't process objective reality, they construct it, filtering sensory data through layers of expectation and memory. If our inner worlds are already curated illusions, why not the outer one too? Yet the theory's real test lies in falsifiability. Some researchers propose experiments with quantum erasers, where observed particles seem to rewrite their past behavior retroactively, as if the universe edits its own script based on future observations. Others suggest searching for cosmic-scale quantum superpositions, where entire galaxies remain undefined until measured, but until then, the consciousness-created cosmos remains a tantalizing, unsettling frontier, either a profound insight into reality's nature or the ultimate case of the universe gaslighting itself. One thing certain: the act of questioning it might be the very thing that keeps the answer real. From black holes birthing universes to cosmic voids where reality itself might unravel, we've journeyed through theories that stretch the limits of imagination. Each one, whether dark matter's invisible scaffolding, the chilling silence of the Fermi Paradox, or the holographic illusion we might call reality, reminds us how much of the cosmos remains a whispered secret, just out of reach. These aren't just wild guesses, they're the frontiers of human curiosity, where science dances with speculation to uncover truth stranger than fiction. Think about it: we live in a universe where 95% of its content is missing, where time might crystallize into repeating loops, and where our entire existence could be a fleeting fluctuation in an infinite void. The more we learn, the more the cosmos humbles us. Every discovery peels back a layer, only to reveal deeper mysteries, like the axis of evil's cosmic alignment, or the phantom tug of the dark flow, dragging galaxies toward something beyond our sight. These aren't puzzles waiting for easy answers, they're invitations to keep questioning, to keep wondering. So which theory grips you the hardest? Is it the Dyson spheres hiding in alien starlight, or the chilling possibility that we're alone in a silent universe? Maybe you're convinced reality is a simulation, or that consciousness itself stitches the cosmos together. Whatever sparks your awe, remember, science thrives on debate. Drop your favorite idea in the comments, let's geek out over the possibilities together. And if you're hungry for more deep dives into the universe's grandest enigmas, hit subscribe. The cosmos isn't done surprising us, and neither are we. Until next time, keep looking up because the next great mystery might be hiding